Check it.
Okay, welcome back. Today we're going to continue our conversation about inverses. Now, if you have two functions, let's say here we have f of x and g of x. Can you tell whether or not they're opposites of each other without actually, let's say, taking one function and finding the inverse of the other? So in other words, you could start with f of x, find its inverse, and then see if it matches this. That would be one way to go, but that's not what we're going to do here, so don't do that, please. What we're going to do is do a test to see if these are truly opposites or not. And it's going to require us to use composition of functions that we learned recently. For instance, if we have a function f of x that, I don't know, multiplies stuff by 3, and we have another function g of x that divides everything you give it by 3, those are clearly opposites, right? And if you create an f of g of x function that does the job of both, what you're going to do is, let's say we have a little conveyor belt machine here. Then you put a number in here, and this multiplies by 3, right? That's f of x. And then you have another machine here that divides by 3, x over 3. A little conveyor belt there. Okay, and you come out this way. Let's say you put a 5 in here. This is g of x. You put a 5 in here, you get 15. Then the 15 goes into here, gets divided by 3, goes back to 5. What you started with is the same as what you end up with. And this would be true for any number. Any number in the universe, any real number, you plug in, multiply by 3, and then divide by 3 would end up being the same number. So you could say that this is true for all x. That if you put in an x, you'll get out an x. Because these two functions, they're exactly opposite of each other, and they cancel each other out. So where one function triples, the other one cuts in a third. And you end up with what you started with. So that means that f of g of x, no matter what the number is, will always be whatever you put in. So whatever x you put in, you get an x out. Okay? Now what if you switch these around? Well, if you switch these around, you get g of f of x. Okay? And that will still do the same thing. So I could switch these around, but I don't really have to. You can kind of see that if you took a number, divided it by 3, and then multiplied it by 3, it would still be the same number. So here's the requirement for two functions to be inverses. If you compose them in both directions, you will get an x for both. Okay, that's the logic behind what we're going to do now. So let's go ahead and try this out. We're going to take two functions, and we don't know ahead of time whether or not they are inverses. Now the instructions say, this is pasted from the textbook, determine whether the pair of functions are inverses, write yes or no. If you write yes, I'm marking it wrong. If you write no, I'm marking it wrong. Because you cannot just write yes or no. You must determine, and determine is the work. I need to see the work. And here's the work. So just to be clear, if I get a bunch of yes or no's on the homework tonight, you're not getting any credit for that stuff. So here's how we do this. And by the way, sometimes you can, like, for instance, these two functions here, you can just look at it and see that they're obviously the opposites. And you might be tempted to write yes immediately. Once again, can't do it, won't get any credit. You have to do the composition of functions here. So let's go ahead and do the composition of functions. The first thing we're going to do is test f of g of x. Remember, if this equals x, then that's good, but that's not enough. You have to then find g of f of x. And if that equals x, if both of these are true, then you can say yes. If either one of these comes out to be a no, like for instance, this turns out to be 3x, or 3x plus 5, or 1/2 x, or something like that. If it comes out to be anything other than x, then it's instantly a no and you can stop working. Okay, but you have to prove that before you say yes or no. So here we go. Let's test f of g of x for this first set of problems here. Now, the first function is f, so we're going to copy this. It's 3 blank minus 1. So 3 blank minus 1. And what goes in the blank is this other function here, which is 1/3 x plus 1/3. You need to see the setup. Now you're going to distribute your 3. 3 times 1/3 cancels out, right? Because the 3's cancel out, you just get 1x, or just x. And 3 times 1/3 is 1. And then you still have this minus 1 on the end there. So you get that. And now these two numbers here, this -1 and this +1, also cancel out. And you get a plain old x. Okay, so far so good, but you're not done. So that's actually not the final answer. So f of g of x works so far as an inverse. Let's try g of f of x now. You have to go both ways to get full credit. So g of f of x, the first function is g, which is this thing right here. So we get 1/3 blank plus 1/3. Okay. The other function is 3x minus 1. 3x minus 1. Now we're going to have to distribute this 1/3. 1/3 times 3 is 1, so this becomes 1x. 1/3 times -1 is -1/3, and then you have this plus 1/3 on the end here. Well, you can see these are going to cancel out, and you will get an x. Once you have an x in both directions, now and only now can you say yes and box that, because that is your answer. All right, let's try another one. How about this right here? Okay, this looks like it should work. You know, 1 multiplies by 8, 1 multiplies by 1/8, which is dividing by 8. 1 adds 12, 1 subtracts 12. So it looks good, but I can't say yes or no until I actually test it. So let's go. F of g of x first. First function is f, which is 8 blank minus 12. 8 blank minus 12. And here is g of x. All right. And now let's distribute. Okay. 8 times 1/8 is 1. They cancel out. And you just get an x. And 8 times 12 is 96. Okay. And then you bring down the minus 12. Now, when you simplify this, 96 minus 12 is 84. So f of g of x equals x plus 84, not x. So this is a big fat no. Okay, a little deceptive. So if you wonder, what's wrong with it? It looks like it works. Well, think about the verbal method. Okay, if you had f of x is multiply by 8 and subtract 12. The inverse would have to add 12, okay, and divide by 8. Sorry, add 12 and divide by 8, which would make it negative, sorry, f inverse would be, you'd start with your x, plus 12 over 8. It would look like this, not like this. So deceptive, right? Looked like it was good, it was not. So don't make any snap judgments. Don't write yes or no until after you've done the work. Okay, so this next one, we'll check f of g of x first. The outer function is f, so it's 2 times the square root of blank minus 5. So here's your blank minus 5. That's where the x would have been. And in that blank, you're going to put this thing here. So it's 1/4 x squared minus 5. Okay. Now we're going to simplify best we can. Well, PEMDAS says do what's in the parentheses first. There's nothing to do in the parentheses. In fact, we can drop the parentheses here because they're not doing anything at all. And you see this -5 and this -5 become -10. Okay. And now you want to square root what's in here. Well, the fact is this is definitely not going to become x because of this -10 here. Now, if these had canceled out, right, if one of these was a plus, this would have worked out nicely. But it doesn't, because you could have then square rooted, but as long as they're both minuses, unfortunately, this -10 makes this impossible to square root. Now, had they canceled, just hypothetically, had they canceled out, can you square root 1/4 x squared? Yes, you can, because the square root of 1/4 and the square root of x squared are both things that you can square root. Okay, what is the square root of 1/4? It's 1/2 times 1/2, so it'd be 1/2. And this would be x. Well, technically it's absolute value of x, but we're not worried about that. And when you cancel those out, this would have worked, right? It would have worked, but it doesn't work because of this -10. Okay, you cannot break up, or you can break up a square root into factors. So we can factor this and factor this if there's nothing here. But the fact that there's a minus 10 here, you cannot break this up. You can't break this up this way. It doesn't work. So you can factor it, and this is not factorable is what I'm trying to say. Okay, so this is a big fat no. Another no. Okay, and that brings us to the next section, which is verifying inverses, this time by graphing. Now, we just used composition of functions to verify inverses. All right, and now we're going to do something similar. We're going to, well, first let's understand the idea here. If you have two functions that are inverses, when you look at them on a graph, they will be symmetrical across the line y equals x. So take a look at this. Here we have this dotted red line here, and the equation of this line is y equals x. And the reason why it's called y equals x, well, there's a couple of reasons. If you think about it as y equals mx plus b, it's y equals 1x plus 0, right? 1x is x and plus 0 is so. And that means you're starting at 0 and you're going up 1 over 1, up 1 over 1, up 1 over 1, and that creates this line here. Okay? Another way to think about it is the y always equals the x and the x always equals the y. So these points, this is 0, 0, 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6, 7, 7, 8, 8, negative 1, negative 1, negative 2, negative 2, negative 3, negative 3. You get the idea, right? So that's why it's called y equals x. So if you have a function, I don't know, I'll just quickly draw, for instance, a parabola. If you have a parabola, its inverse will be a reflection across this dotted line. In other words, if you were to fold this graph, if this was paper and you folded it on the dotted line, you would have another graph that would land right on top of it. If you folded the paper right here, these would land on top of each other. There's a symmetry across this diagonal line. Okay? And another example might be if you had a, I don't know, if you had a square root function, which we're going to learn about next section, that looked like that. Well, there would have to be one that would look like this. Once again, symmetry. Okay? So we're looking for that symmetry. We're going to graph a function and graph its inverse on the same graph, and we're going to look to see whether or not there's that symmetry there. So we'll start off by finding the inverse. So we have f of x is 2x plus 1, and we want to find its inverse. I'm going to use the swap method instead of the verbal method, just because we want to practice that a little bit more, and the verbal method is pretty easy. Everybody has a good handle on that usually. Okay, so the swap method is write this as y equals, and then solve, and then swap the x and y. So this becomes an x, and this becomes a y. All right. And then we need to subtract 1 from both sides. We get x minus 1 equals 2y, and then divide both sides by 2. And we get our inverse. Y equals this, but of course it's not going to be called y, it's going to be called f inverse of x. And it's x minus 1 over 2. Okay? You could also write it as 1/2 x minus 1/2, but that's neither here nor there right now. So we have our inverse. Okay? First find the inverse. We did that. Now what we're going to do is we're going to graph the function. Now this is a y equals mx plus b function. You could very easily say, all right, the y-intercept is 1. So you start here. And then the slope is up 2 over 1. And you go up 2 over 1, up 2 over 1, up 2 over 1, up 2 over 1. And then going the other way, it's down 2, back 1, down 2. You know, this is, we already have done lots of stuff like this, and you did a lot of stuff like this in Algebra 1, right? But for the sake of finding inverses, we're going to actually use a table. So we're going to go kind of retro here and go back to Algebra 1 and write a table for the original function. The reason why we want a table is because we can use a swap method to swap the x's and y's and get a table for the inverse very, very, very easily. So there's going to be your inverse there. So let's make a table. Let's see. We'll start at, I think, if we go back to like -5. Well, -5 would be -10 plus 1 would be 9. That'd still be off the graph. So let's say -4. -4, -3, -2, -1, 0, 1, 2, 3, 4. And we're going to plug those into the function here. So this would be -8 plus 1 is -7. This would be -6 plus 1 is -5. -3, -1. This would be +1. This would be 3. This would be 5, 7, and 9. Yeah, which is off the graph because this graph is only 8 by 8. So we won't do the last one here. Okay, so we have our table here, and we can do our graph here. So -4, comma -7. That's -1, 2, 3, 4. -7 is down here. -3, well, here's the thing. We don't need to draw every single dot because this is a line. This is linear. So really, if we just do the first and the last, we're good. So 3, 7, 1, 2, 3, 7, that would be right there. And the other points will be in between, but once again, it's a line, and we're about to use a ruler here, so we could save a little time and just do the first and the last. Okay, there's the function. This is f of x. And now we want to find f inverse of x. Okay, so f inverse of x, we don't know what that looks like yet. We don't even know if it's a line. So let's not make any assumptions here. What we can do is look at the table here and say, all right, we'll use a swap method. And instead of -4, 7, we can go 7, -4. And this will be -5, -3, and this will be -3. Just swap the x's and y's. And now we'll start drawing that. So -7, -4, -5, 3, -3, -2, -1, -1, that would be right there. 1, 0 would be right there. 3, 1 would be here. 5, 2, that's 3, 4, 5, 2, and then 7, 3 would be here. And yeah, it definitely looks linear. And since this is the inverse, I'm going to do it in green. And now we look at it. Are these two functions reflections across that dotted line right here? And it sure looks like it. Okay? In fact, I've created a Desmos demonstration here where here's the original function right there, and here's the inverse. Okay, so this is a little bit cleaner than, well, not much cleaner than what I did on paper here. Okay, so there's Desmos and there's what I did, and you can see, yeah, it's pretty clear that this is a reflection. Okay, the distance from here to here is the same reflected. They meet at a certain center point here, right there, and then they keep reflecting. So yeah, it looks like these are inverses visually. Okay, I mean, you can't tell things precisely visually, but you can get a pretty good idea. So this is f inverse of x. This is f of x, and you can see they are reflections across the line y equals x. Okay, let's try another one of these. All right, we want to find the inverse of x squared minus 4. So we'll use the swap method again. This is y equals x squared minus 4, writing it as a y equals function first. Then we'll change all the x's into y's and all the y's into x's. So swapping there. And now we need to get the y by itself. So we'll add 4 to both sides. That'll cancel that out. We get there. And now we square root both sides. Now when you square root both sides, this becomes the square root of y squared is absolute value of y. And when you drop the absolute value bars, that creates a plus or minus on the other side. So what you get is y equals plus or minus the square root of x plus 4. And now we'll replace this with the correct name. It's not y, it's g inverse of x equals plus and minus square root of x plus 4. So what does that mean, plus and minus? There's actually going to be two functions that will function, or that will that will be the inverse of this thing here. Now this, if you look at this, this is a parabola that shifted down 4 spaces. Okay, remember your parent functions. X squared minus 4. So you just go down 1, 2, 3, 4, and you got yourself a parabola like that, right? So we're going to be a lot more precise. We're going to make a table. And since we're squaring the x's, we can't put in very big numbers here. I'd say, so we'll just go -3, -2, -1, 0, 1, 2, 3. Anything bigger than that would just be too big, I think. So negative 3 squared is positive 9. Positive 9 minus 4 is 5. Negative 2 squared minus 4 is, well, it's 4 minus 4, it's 0. So yeah, there's a symmetry there you can see, and that's because a parabola is a symmetrical thing. So let's graph it. Negative 3 comma 5, so negative 3 comma 1, 2, 3, 4, 5. Negative 2 comma 0. Negative 1 comma negative 3. 0 comma negative 4, right there. 1 comma negative 3, there. 2 comma 0, there. And 3 comma 5, there. And you can see it's very symmetrical. Okay, so there's our parabola. Now here's the problem though. There are two functions here, not just one. There's the plus square root of 4, x plus 4, and the minus 1. So we're going to have to make two tables because there's actually two parts to this inverse. So g of x, g inverse of x, the positive one, and then we have negative g inverse of x. Okay, and we're going to have to make two separate tables here. So we're going to start with, we'll start with negative 4 because negative 4 plus 4 is 0. So we would be starting at 0. If we started with negative 5 plus 4, that would give you a negative 1 and you can't square root that. So going to negative 5 just won't work. So we're going to start with negative 4. So negative 4, negative 3, negative 2, negative 1, 0, 1, 2, 3. We'll stop at 4, I guess. Actually 5. Because 5 plus 4 is 9, you can square root 9. And then we'll end up doing the same thing here. Negative 4, 3, 2, 1, 0, 1, 2, 3, 4, 5. Now, here's the thing. That's a lot of numbers, and that's a lot of plugging in. We don't want to, we don't want to use a calculator for this. We don't want to use any decimals. So what I'm going to do is, I don't need a whole lot of points to graph this. I just need a few good points. So what I'm going to do is only take the points that are whole numbers. They're called lattice points, okay? So we're only going to use the lattice points to graph this. So, not lattices, lattice points. And you'll see which ones are lattice points, and those are the ones that I'll use to do the graph. So if I plug in negative 4 plus 4 is 0, and the square root of 0 is 0. Okay? That's for the plus and for the minus, so I can do it for both tables. If I plug in a negative 3, negative 3 plus 4 is 1. Negative 3 plus 4 is 1. Square root of 1 is still 1. So this would be 1. And on the negative version of this, it would be negative 1. So I can do both tables at the same time. That's the good part about this. Now, for negative 2. Negative 2 plus 4 is 2. The square root of 2 is a decimal. I'm going to skip that because it's going to be an irrational number. And I don't want to go to 1.41 whatever, okay? So I'll skip it because it's a decimal. Negative 1. Negative 1 plus 4 is the square root of 3. Square root of 3 is irrational, meaning a crazy decimal. I'm going to leave it alone. How about 0? 0 plus 4 is 4, and the square root of 4 is 2. That one works. And for the negative function, this will be negative 2. All right? Now, 1 plus 4 is 5. Can't square root that without getting a decimal. 2 plus 4 is 6. Can't square root that. 3 plus 4 is 7. Can't square root that. 4 plus 4, can't square root that. But 5 plus 4 is 9. Square root of 9 is 3. And for the negative function, it's negative 3. That's why I went all the way to 5. So if you're thinking, why did he use so many numbers? Because I wanted to get a few good lattice points. All right? And now I can graph these. So let me graph them in with the green pen here. Negative 4 comma 0. Negative 1, 2, 3, 4 comma 0. And that point is actually the same for both of these, right? And then negative 3 comma 1. So here's negative 3 comma 1 up here. And on the other function, it's negative 3 comma negative 1, which is down here. And then 0 comma 2 and 0 comma negative 2. So 0 comma 2 is here, and 0 comma negative 2 is down here. And then 5 comma 3 and 5 comma negative 3. So 1, 2, 3, 4, 5 comma positive 3, and 5 comma negative 3. So you can see, because I did both of these functions, I'm going to get both sides of this inverse. I'm going to get the side that's here, and now I'm going to get the other half of the parabola on this side. So if I hadn't realized that there's a plus or minus here, I only would have had half the inverse. Now let's go over to Desmos and see what a cleaner non-sketch version looks like. Here's the original function, okay, just to compare it to that. And here's half of the inverse, Okay, that's the positive square root function right there. And then here's the negative square root function, which will be the other half. Okay, and you do get that same kind of heart-shaped or whatever that you want to call that. Okay, so we're done, but just to summarize here, you have to do 3 things for these problems. 1, you have to algebraically find the inverse, which I did here. 2, make a table for the function that you're given. 3, flip that table using the swap method, and then graph both of these on the same set of axes. Okay, we're done. See you at the next video.
Check this.